inconvenient, but we don't have too much choice now, given the fact that. So sorry for late start. We'll cut the break short. So let's quickly go over that. The goal of today is we want to finish this hypothesis testing and start from ANOVA. Okay. So I'm not going to review the because of time. I'm not going to review in detail what hypothesis testing. I think it's already very clear from now on. It's basically you have some idea on how the mean looks like, and then you really want to see the data support our hypothesis. Okay, I just quickly with the two sample idea. The two sample idea is the following. Okay, let me draw a picture. I think that would be easiest, right? So the idea is that you have, say, the example would be I have bunch of boys and bunch of girls, right? A bunch of boys, right? Okay, population 1, and I also a bunch of girls. Okay. Suppose I want to see if boys and girls have different willingness to pay for the product, right? How much they want to spend on the shop, they can be different, right? So the question would be underline all the girls, the mu2, right? And that's what we care, right? Because how much on average they want to pay is the way that we design how to sell a product, right? Man is mu1, right? And the way we do is the hypothesis we want to test is if mu1 equal to mu2, right? Or mu1 not equal to, right? Or you can do mu1 more than or mu1 less than, will be the same. But we focus on the case of this. I think it's easy for you to see how you extend when it's one-sided. And the idea is that we assume, right, that the underlying is a bell curve, right? There's a bell curve, how much to pay, underlying is a bell, right? And then what actually we do is to collect some data here, right? And what is the X bar 1 is also a bell, right? Because this is a bell, this is a bell, right? The idea is the other is a bell. The sample mean is also a bell, right? And the bell actually depends on the sigma square 1 over n, right? Sigma square is the how spread the number is, right? And of course, it will center at mu1, right? And similarly, we have the same idea here, right? Assuming the underlying is a bell, right? How the woman spend on the product is also a bell. And that means that when we try to draw some sample here, right, it's also a bell. Right? It's also a bell with mu1, right? So mu2. With mu2, sigma square 2 n2, right? Depends on how many sample you got. Okay. And how are you going to test this hypothesis, right? The idea is looking at, hey, since you're looking at the population mean are the same, right? And since they're all bell, right, we know that this is going to be the bell as well, right? Because difference of bell is also a bell, right? And the location of the bell will be mu1 minus mu2, right? And the shape is just sigma 1 square over n1 plus sigma 2 square over n2, right? So that's the shape, okay? And if you say under the null, this is 0, right? And the question is looking at our data, look at x1 bar minus x2 bar, what are those, right? If it is too far away, which other color, right? It's too far away, either here or there, because two-sided, right? If one side, the same idea. It's two-sided, then we will reject the null, right? So suppose we found out that, right, men spend much more than women, right? Then reject it, right? Or women spend much more than men, then reject it. Only if they're very close to each other, then we will not, right? And the size, how far is so far, right? Remember, is use alpha over 2 here, right? That's the way we have been doing all the time, right? And if we know sigma 1, sigma 2, then we're done already, right? Because shape is well known, right? There's no nothing you need to do further. Suppose we know sigma 1, sigma 2. But the problem is, in general, we don't know. Okay? So that means that we need to use the T, okay? It's a T, convert to T, and use the some version of do the shape, okay? And suppose the general case is we don't know whether sigma 1 equals sigma 2, okay? General case is we use S1 square and S2 square, right? S1 square as estimate sigma square 1, right? S2 square sigma S2, right? And this is T of degree freedom V, right? And V is a very complicated object, right? Which table we look at is a very complicated object. But we know that it's very simple, right? We just look at the same thing, right? Look at here and there, and we're done, right? That is the way that to do if I don't know, I don't have further assumption, right? If I further assumption, say sigma 1 square is equal to sigma 2 square equal to sigma, right? In that case, both S1 square and S2 square is good estimator of sigma, right? So we have to find some way to estimate sigma, which is called SP square, right? Some combination of that. And you also check the T table, but we now know is N1 plus N2 minus 2, right? And everything is the same, okay? So that is what we have, okay? And that is the first one. The other one is called the paired population, okay? Before, the boys and girls are unrelated, right? But now with example, I probably give the same example last time, right? It's 1 and 2 population are paired, okay? It's saying that a guy here, right? He's single. Now he got married, okay? We're asking how happy he is or how much time he spent on playing computer games, for example, right? The same guy, okay? Guy number 1 here and guy number 1 here, right? And we have another guy number 2 here, okay? Okay, and guy number 2 here, okay? And he also got married, right? We asked after he got married, how much time he spent on playing computer games, or for example, right? Okay. And what we care is this number, right? Is the notation we have x11, right? And is x12, sorry, x21, right? How much he spent is x12, and how much he spent is x22, right? What we care is the difference, right? Because we can pair exactly who is who. So what we care is D1, which is x21 minus x11, right? And we care this, D2 is x22 minus x12, right? So look at before and after, right? Before the man got married is x11, the one guy. X21 is the guy who got married. How much time he spent on playing computer games, right? The difference, right? We care about the difference, okay? And if we assume that these, right, follow the bell curve, right? How much they spend on paying, the changes is for the bell curve, right? Then with some sigma square, right? That means that the sample mean D bar, right, will follow a bell curve with some mu mean D, right? Mu D, right? And would be sigma square over N, right? If you know the sigma square, then we just do the standard normal, the standard Z test, right? If we don't know that, we do the T test, right? T is N minus 1, right? Right, we do that. So if it's just too much or too small, then you reject, right? If the same idea, right? There's nothing new, but you just look at the difference, right? The difference is a new variable, which we just use just one sample T test or Z test, depend on whether you know sigma or not, okay? In the slide, I focus on the case where we don't know the sigma square, but in case we know sigma square, then we are okay. Is that clear? Is that clear? Maybe I switch the mic because it seems like it's not working very well. So let me pick out the mic. I think I accidentally lock it, so I have to wait a few seconds before I can do that. So that would be the paired. Okay. So now we quickly do the last two. One is we talk about proportion. So here we talk about pair. We talk about this. Okay. Before we do that, so it's very simple. We try to look at the problem like this. Okay. Population 1, we're looking at how many, say, how many people, say, suppose one is New Asia College. Okay. We look at how many female, male, female, male, right? And we also want to compare, say, where we are, right? 2 is United College, right? We can look at female, male, female, male. Okay. The question is it more male in New Asia College or more in United College, right? Or you can imagine the simple example would be you want to see not the college, maybe you want to see maybe this is Hong Kong, this is Kowloon, right? And you can see whether we have more men than more women, right? Or more business application, maybe you want to look at how many people like your product, right? Or you have two products, product A is blue color, product B is red color. You want to ask different group of people whether they like you more, right? Why we care about that? Because as again, you want to have a product marketing strategy, right? If people in group 1 like red color more than other group, then you do other way around, right? Just like people like, suppose you're selling cars, right? Maybe one country they like a petrol car, the other country like electric car, then you would do different thing, right? So, and the idea is nothing different there, okay? It's same as what we do to independent population. And the only complication or the only simplification we have is because now we care proportion, right? So this is called pi 1. Let me use other color because green here, right? And the population, how many people there is called pi 1, right? And how many people there is called pi 2, right? And do note that when we have this pi 1, this is the mean, but we also fix the variance. Hopefully you recall that. That is called the proportion data. Is like a special thing. Okay, and the special thing is if you try to collect some data here, right? This is called sample proportion. You know the shape already, right? You know if the mean is pi 1, right? And the variance is pi 1, 1 minus pi 1 over n1, right? Suppose you draw n1 out of here, right? Similarly, then, and this is also a normal, okay? The same idea goes on here. Suppose you pick up n2 of here, right? You already know this is going to be a normal, right? This is pi 2. The sample proportion will be centered at pi 1, sorry, pi 2, right? And the variance will be pi 2 over pi 2 over n2, right? So we know it's a bell curve, right? Because it's when n is large enough, bell curve is sufficient, right? Remember, that is one special case here. And the thing is, we want to look at, again, the question is, look at whether the two groups are the same. Sorry. Pi 1 is equal to pi 2, right? And this is pi1 not equal to, you can do both sides, but I just focus on the same case because they're normal, right? So P1 minus P2, right, would be just Bell. This pi1 minus pi2, right? And the shape will be pi1 minus pi2 over n1 plus pi2 1 minus pi2 over n2, right? Just add them up. The variance are add up, right? That's how the formula is. And again, the question is, okay, if this is too small and too large, then you reject. Look at your data, right? If the man and woman in this case is too much different, then you reject, right? The same idea, nothing new here, right? The only new thing here is much easier because things become easier. Let's see the formula, okay? Because that will be easier to look at, okay? In the case proportion, right? And this is what we have, right? The same. This is exactly the same as the formula that we have here, right? If you remember this formula, not the pool one, but unequal. This is the same as this one, right? The only difference of this, remember the proportion and the case is now we no longer need the t because we can use just p, right? It's normal. Okay, it's a normal. The only difference is normal. Okay, and the question lies on the fact that if they're the same, right, under the null, right? If pi1 equal to pi2, right? So go back to here. The only complication here is if under the null they're the same, right? That means that this pi are same, right? And we can easily estimate pi. Why? Imagine pi1 is what? Pi1 is proportion of man or woman in New Asia College, right? And pi2 should be the man and woman proportion of man, right, in United College, right? So what you can actually do, right, for estimation, right, you can just forget about the distinction of NA or UC, just add how many women out of the total, right? So that is the formula you see there. It's this one. You add up how many men or women, depends on what you say, over total number. That is our best guess, right? This is our best guess of P or best guess of pi, right? In that case, just do that. So this is actually similar, more similar to the case of equal variance, right? So it's similar to this case, right? It's because they're the same. So similar to this diagram, right? This one. But instead we have n here. So it's normal here. So that is the only part that we are doing. Okay. So let's go to the example. Okay. But before we do that, I do want to emphasize one thing, very special thing, is here we have the, only in this case, okay, the confidence interval estimator is different from hypothesis testing. Okay. Usually, you would put the denominator for this one, right? But now we don't have this because that is only possible when they're the same. Okay, so we can't redo that. We have to use our own version. So that is the first incident that there's some disconnection between hypothesis testing and confidence interval estimate. Okay, so that is some part that I want to emphasize on, but rest are very similar. So let's do it and show that to you that that will be the case. Okay, so let me do it on the paper here so that you know what I'm looking at. Okay, so the question again is like two sample. Okay, as I said, this is NA, right? And NA, how many people I get? I got 50 people out of NA, right? And I don't know what the pi one is. There's something I want to know. But how many people? 50 people out of the people, I have 60 of them, right? Means 30 of them, right? 30 of them are, say, female, say, okay, like a proportion of female, okay? So that means 20 of them are male, 30 are female, right? And I also look at UC college, okay? And out of this, I pick up 40 people, okay? And proportion of female is 0.7, okay? That means what? X2, how many people are female? 28, okay? So now we go to solve this question, okay? The idea again is we want to see if I want to see number of female in two colleges are the same or not. Okay, so this is the question. Okay, this is the problem. Is that clear what we're asking? Right, we want to see, is it the same proportion of females in the both college? Okay, is that clear, the question? Okay, and remember the formula, okay? First thing is under this is true, okay? Under this is true. It means that there's no difference between two college, right? You want to guess the overall, suppose this is pi, right? And we want to guess it by P, right? Or P hat, right? How many women are there, right? In total, we have, how many people we ask? 90 people, right? And out of which we have 30 plus 28 people that are actually female, right? So that's why it's 90 over 58, okay? So that is our guess. If that is upon estimate, right? Because the same, we don't need to distinguish who is who, right? So, but now with the grouping, so the question we want to see if the grouping are different, right? So we want to see, the question is, we have P1 minus P2, right? The sample proportion, remember, it's a random variable, so we have a bell curve. So we have a bell curve here, and the center under this null is 0, right? There should be no difference, okay? And we would worry if there's too less or too much, right? And how do we proceed, right? But we know that, okay, the variance will be pi 1, 1 minus pi 1 over n1, right? Pi 2, 1 minus pi 2 over n2, right? And if they're the same, under the null, they're the same pi, so we don't have to have the 1, right? We don't need the 1 there, right? And this is the best estimate, so you just put that there. Okay, and we can convert to Z. Okay, so look at this. The data we have is 0.6 and 0.7, right? So the difference is actually negative 0.1, right? The question is negative 0.1 is here or actually is here. So the question is like this, right? Is it within the far away region or close enough region, right? The region we define is, again, alpha over 2, right? There's nothing new there. So that's why we have repeat many times. I hope this is very clear, right? So basically, it's just like you draw this shape here. This is 0, and this is Z, right? This is Z negative alpha over 2 here. This is Z alpha over 2, right? You just convert this guy to here, right? How do you convert that, right? You just, how many SD here, right? So this over the square of that, right? The distance over the square root of this, So the number here go down, or the number here, right? Just this number over the ST. So negative 0.1 square root of this guy, right? You know N1, N2, P put there, you're done. Okay? So that is, let me go to the slide. You will see that, right? Here with the number we have already set here, right? So just put in the formula there, right? It's the same as what we have just said. This is just 1 SD, right? 1 SD from the mean. And you know 1 SD from the mean is not enough, right? 1 SD from the mean is actually too far away. No, too close to 0, right? Or too far away from the rejection region, right? And that's the case. Okay, I don't think I need to repeat because it has repeating myself too much times. Okay, so what is left is have to remind you is when you do confidence interval, make sure that this is not using the p pi. Okay, use the one actually from your p1, p2. Okay, that's the only difference. This use p1. This is 1 minus p1. This is p2, 1 minus p2. Okay, the rest are the same. Okay, so is there any question? So I'm sure that you would have some question, but let's have a break of maybe short 5-minute break, because I think then I'll go around to answer any question that you might have. Okay, that's a break of short break. I know a little bit fast today, but it's the same thing, right? Nothing new there, right? Just what we are doing is just, if you imagine, right, what we do is just like, before we do proportion, just one guy, right? Now we care the difference, right? One guy proportion is a bell curve. Difference of the two bell is still a bell, right? So the only careful is the variance is no longer just one, you have the two variants. So there's a new formula here, okay? That is the only new thing there, but otherwise, everything is pretty straightforward, okay? But that being said, I'm pretty sure that it is not easy to understand unless you actually work on exercise, okay? So I recommend if you have time, you should go home and work out the assignment. That would actually help you to see if you got it or not gotten it, okay? So I'm setting up the U reply, and then you can tell me how things should be done, but is it too fast or too slow? But in the meantime, I go around to send a question. So we will take a short break. So let's resume maybe a little bit more than 5 minutes, 6 minutes, 8 minutes, maybe easier, right? A little bit longer. Let's resume at 3:26. Testing. Oh, much better, much better.
we will still do this is separate. This is common level is what we estimate. Suppose I ask you what is the price of the you tell them what is your guess. Yeah, the separate one, this is estimation. The other is common level the last about estimation. Technically, this is not yeah, you will do that cycle. You do it all. Binary data or mean sample. Sample đại là này cái gì đó là này trả lại sample người sample này thì chúng ta đeo rồi cái sample của chúng ta đeo rồi chúng ta đeo cả hai cái đeo個分別就係如果係冇講計出嚟結構嚟講，冇需要得嘅，同埋你個 variance 去計出嚟，你計一樣嗰陣時咧，如果你係男嘅，個兩個都係一樣嘅，咁你咪可以淨係計所有嘅啲你佢都係做你計佢overall嘅狀態嘅，咁你個偏差。 some that example actuarial variance. Central convenient. Welcome.
So the question here, can I explain more about T-table? Yeah, I can. So T-table, I guess I upload the tables in the Blackboard, right? So because someone asked me from another section, they want me to upload a table so that you can print and bring to exam. So I just prepared the table. Okay. So some people ask me how to check table. So this is a set table, but some ask me the T table. Oh. Okay. The T table, I gave you the one is this one. Okay. The T table I give in the slide is this one. Is middle is 1 minus alpha, right? And the number I give you is actually T sub alpha over 2. Okay. So that's how I look at it, and they actually give you the critical value, right? In that case, right? Actually, the critical value, and that's how this table being used. Okay, and probably you want me to show you how to use them, right? So let's go back to the example. Let's go to some example and illustrate how you use it. Okay, go back to the case where we have the say is the boys and girl question, right? Just to remind you, what's the question here? The problem is this one, right? I want to look at how men are spending their time, right, online, okay? And we don't know sigma, so we have to use T, right? And in that case, okay, look at this problem again, right? What we have is 16 sample, right? The D bar is a normal, that's assumed, right? And the treatment effect is 0, okay? And what we have is just 1 here, right? And we don't have sigma, right? But we have S, right? We have sigma square over N, right? And if we replace by S, right? That would become a T, and minus 1, right? That's what we do. And turn out that this is 2 here, okay? And the question is how to use this, right? And of course, you can find this value, right? By using 1 minus T this, right? And then 2, and then 15, true, right? And that's the case. But if you suppose you don't know how to do that, right? But of course, all I do if because I do it two-sided. And suppose you don't do that, right? You have to figure out what is the 5%, 2.5% here, right? Suppose alpha of 2 is here, right? And alpha is 5%, right? So look at the table again, okay? Look at the critical value, okay? Then what we're doing is looking at look at this one, okay? We look at 5%, so we look this column, okay? And because N is 16, so we look at the 15 one. So it's 2.13, okay? So is inside that, so we fail to reject. Is that clear? Is that okay? Okay. So that's how we use it. And this same as what I said, right? And now the next question, I hope that is okay. Yeah, today we have all people know is compare proportion. So everyone knows it, and that is something we learned today, compare proportion. The speed is okay, luckily. I'm pretty sure that everyone would somehow is not concrete, we cover. Because we cover so many formula, but that's you don't want our class, basically I go over all the example again, right? So you have to try to work out some of the assignment. Hopefully you learn how to work it out. Do you know whose cat can't be eaten? Oh, that's one. Oh, it's kid's cat. Why? Because kid cat. Oh, can be eaten. Okay, kid cat. So it's fun. What is biggest red flag in the world? Oh, China. Is it? Oh yeah. But what about Vietnam? I don't know. Which is bigger? Assignment is hard. Not sure it's hard because just applying the example. So it's testing how you know it. As I said, the TA cannot give you how to do it, but he able to point out what you can look at, and you can just simply ask. And I advise you also talk to your classmate as well, right? You can do it as a peer. I mean, of course, you have to submit your own work, but I recommend that you try to do it yourself. Otherwise, you don't really learn it, because at the end of the day, this is a math thing. Sorry. It's a math thing. Okay. I have to do this. I mean, very annoying. But so lastly, we introduce something a little bit new, less boring, but it will be very similar. So the final test we are working on, don't worry, this is super simple. Okay, I mean, it can as simple as you would expect. The simplest hypothesis test you are doing. Okay, the question is why we don't do this first. Why we save the easiest to last? But I don't know. The textbook is doing like this. So I have two samples. One to want to see is the variance of the two samples the same or not? Okay, very simple question, right? Let's go back to draw it, right? So the question like this, right? I have one group of people, okay? How much they spend, I don't know, okay? It's a normal, okay? With some mu1 and sigma 1 square, right? Do note that when I do this, it's talk about how people looks at. There's no probability here, right? There is probability if I just randomly draw one guy, okay? But there's no probability here, right? Guy number 2 here, probability number 2 here, right? I also have this, right? Mu2 and sigma 2 square, okay? And the question I want to know is, I don't care about that mean the same or not. I want to care about they are the same variance or not, which is a valid question. Imagine application of, I want to know, is it method 1 more accurate? I mean, say, example, method 1, say, population 1 is a stock 1. Population 2 is stock 2. I want to know is that stock 1 is more riskier than stock 2, regardless of the mean. I don't care about the mean, right? There's something we ask, right? Later you will see we'll use it to ANOVA today, but that's the only thing I want to compare. Sigma 1 square is equal to sigma 2 square. And in the case, it is not. Okay, this is something I care. Very simple, right? And turn out that if they're normal, very simple, they will follow called the F distribution. So you simply, what you do is simply divide the sample variance and you're done. Okay, because you collect the sample, right? In the case, you collect some sample here. How many sample you have? N1. This is sample variance. Okay, and I need to check from here. I collect how many sample I have, N2. The sample variance is S2 square, and I just do the ratio. I'm done. So as I said, it's very simple, right? Just look at the dividing it. But the only complication lies on the division. Okay, follow the F, but F has too many tables. Okay, and which table you're looking at? Is the table looking at the F, N1 minus 1, N2 minus 1. Okay, you're looking at the table not only have one dimension, you have two-dimension table. Very complicated, right? Because T will have the first table, second table, third table, right? You look at N minus 1 table usually, right? But F is very complicated. Not just look at one dimension, 1 up to N. Okay, you have to look at, okay, just imagine that, right? T table, you just look at. There is a line there, you just pick up a number there. But F table is two-dimensional table. You tell me how many sample N when looking at 2F and pick up the right table, right? So it's not a table along the line, but it's table in the area, right? You go by row and column, pick up the right thing. Okay. So don't worry. I'll illustrate the example, then you'll be very simple. Okay, don't worry about that. And the other complication about F is what we call last time is not symmetric. Okay, it's all positive, then usually look like this, depends on N1, N2, but it's start from 0, go to infinity. Okay, so to check this, you have to check left and right, you have to check 2 times, okay? But don't worry, it will be simple, okay? Let us go to the example, so don't worry, it's super easy, okay? Super easy. The question is that, okay? We have first sample, use blue color, right? We use N1 is 50. sample variance, S1 square is 30. Okay. And the other one we have N2 is 40 and S2 square is 20. So this is a question, right? We simply want to compare the variance, right? And as I said, very simple, we don't need to even do anything. S1 square over S2 square usually follow this type of graph. Okay, this type of graph. So you simply take a difference. Tail is 1.5, right? 30 over 20. That's so simple, right? 1.5 here. The question is, I do a two-side test. Okay, one side with same idea. Means that I want to put 5% separate into both sides, right? So what I want is 2.5% here and 2.5% there, right? Or I want to do the critical, this is a critical value, right? I want to see if 1.5 is actually within or outside, right? So what we're going to do is same as what we have done so far, right? The only troublesome is we need to look at them both, because different from T or Z, they're symmetric. I found one, the other is found, right? You have to find both, okay? But it's not complicated, right? See here, left-hand side 2.5%. So just F dot inward, okay, 0.025. Now, N minus 1 is 49. N minus 2 is 39. Then we're done. Okay, give you this number. Okay, and for this one, right, the right hand side 2.5%, left hand side is 97.5, right? So just F inverse, right, 0.975, 49, 39. Turn out this number, right? Because 1.5 is between them, you don't reject. If it's outside, then you reject. So it's super simple. And usually you don't do p-value for F. Usually you don't do. Because for the two-sided one, it's slightly more complicated. Usually don't do. Just do the critical value, then you're done. But we can do that, of course. But I guess it's the computer can give you directly, but I don't want to bother with that. Okay. Now, that's the end for the Harbor testing. But before we do that, I want to show you Excel how to do all of those quickly. But before we do, let's end here first. I need any question before I go to Excel. Excel can do everything we just said about the two-sided test. Yes. Yes. So what we know from this, we do not reject, right? So they're the same. Then that means that we can do the t-test where when we find difference, have equal variance. That's usually how it will do. Okay, but I don't talk about this because I don't want it complicated. But usually the procedure is after this you're done. Okay, you do the two t-tests. You can assume they have the same variance. Okay. Oh, if application will be first, if the stock, you would say the same variance, same risk. Variance accuracy, right? If you want to say two different machines have same precision, that's what you're doing. And of course, when we talk about ANOVA, that is the one application later we talk about soon. Okay, after that. And the second application, as I said, you do the t-test. you want to assume the same variance, that is usually you should run this F test first, and then you can do that. But I don't want to talk about that because it's a little bit way above our thing, because we use F in other contexts, but that will be the thing. Okay. Very good question. Any more question? Very good. Very nice. I mean, so if no, then I will tell you, something is like, I have 1 and 2. If I reverse with the same, here is I reverse it, you get the same conclusion, right? Because what I call 1 and call 2 the same thing. So everything is symmetric. The p-value is too complicated, so I don't want to talk about that. So you can safely ignore the p-value, because the p-value involves some minimum of stuff. Then basically it's just like the p-value will be looking at the area on the left, on the right. Look at the minimum, multiplied by 2. But I guess it's too clumsy for you to learn that, so I just skip that part. The critical value method will be sufficient for your purpose. But what I want you to focus you on is on to do the test in Excel. So I don't want to talk about the t-test, because the t-test is exactly what we have here. Okay, so the t-test, t.test is Excel. If you give him x and x1, x2, which is list of number, and you tell them is right tail or left tail, it's one tail, left tail or right tail. Okay, and equivariance is just 2 here. Okay, then they automatically conduct a 2-sample t-test, okay, to see if that's the case. This is the data you have, right? Is the p-value. Okay, this is what you can do it if you have data. Okay, just like this example here. Okay, I have the test here. I have the two set of number here. Okay, and you can simply call t-test. Okay, right tail. Okay, you'll be testing the right tail the same. You can do the t-tail, 2 tail, or the left tail. Left tail with 1 minus the right tail. Okay, so that will be the, if your data, this will be a result. So it seems to be you want me to run it because it seems like everyone is like, oh, what am I doing here? Okay, let me do that. Okay, let me do it. So what they're doing is, so far, the example what we saw in this slide, right, is don't start with data, right? What we have is, okay, I give you the sample mean, I give the sample variance, and so on and so forth, right? And you calculate directly. But Excel is good is you don't have to do that. You can do it by scratch. So suppose I have sample 2 here, right? Suppose sample 1 have some data here. I don't care what the number is. Okay, I just randomly put. Okay, what I want to do is I have 2 sample. I want to see if they're the same mean, right? Suppose I want to do the 2-tail test. Okay, it's very simple, 2-tail test, right? Then I do the 2 t-test, 2-tail, okay, with equal variance, right? So that will be t dot test. Okay, I put x1, x2. I tell them it's 2-tail, 2, and 1, 2, 3 tell me is paired, equal variance, or unequal, right? If I do unequal, it's what we want, right? That's the solution. It's 2-tail. Okay, this is right. So if you want to do equal, right, you just use unequal, then use 3. So this is equal variance. Okay. And you can do the same, right? Unequal variance. How do we do that? Right? It's just t dot test. Okay. And I just highlight the data I have. Right? And I do two tail, one tail the same. And I do unequal variance, lose 3 here. I'm done. You can see not much different anyway. Right? So the next is I want to do the paired t-test, right? In that case, I only care about the difference, right? Each one can be paired. So I only use this data, okay? I don't use the last two because it's not paired. Okay. So how do I do that? T dot test. Okay. A7 to A6 and B to 7, right? And I do two tails, say, I do pair. Okay. So that is how I do that, right? So we're done already. Right? There's nothing very special. Right? So that is how quickly Excel can do things for you. Right? Of course. In the slide, I tell you that how my equation is equal to that, right? You can see then you go back to the slide, right? And you can see that I actually calculate all the result, how this can be equal to that. Okay, but I don't think I need to do it. Last and F test, I want to show it as well. So F test, I want to see this F test, right? To see that the same. So F test, right? I put in this one, I put that one. Okay, that's with F test. Okay, bless you. So that would be the answer. Okay. So do note that this p-value is a p-value, all they get the p-value, right? So if less than 5%, then you reject, right? So in this case, F test tells you that the sample variance are not different. Okay, is that clear what we are doing? Okay, I will upload this file, but there's nothing different from too much different from what we have already. Okay, is there any question? No. So don't worry, the rest of the course is just applying another boring formula. Unfortunately, there's nothing very new here to learn. Okay. Just a bunch of formula, but I try to make it more interesting. Yeah, hopefully. So let me talk about what we are doing for analyze of variance. Analyze of variance is basically the following. Recall what we're doing. What I have is a bunch of boys. So far we've done, right? Bunch of boys. Okay. And I ask how much they spend on the product or stuff, right? And I ask a bunch of girls and how much they spend, right? What I want to know, the null hypothesis is, okay, is mu1 equal to mu2, right? And the null is mu1 not equal to mu2, right? The assumption is underlying is a bell here, this is also a bell, right? Okay, so that's assumption. We have been doing like this. So the question of ANOVA is simply go from 2 group to more than 2. We have 3 groups. Okay? Suppose you have a group of old men. Okay? You want to ask mu3 here. Is it the same? Okay? then it means at least not all the same. Not all the same. Okay, so that's a question, right? So simply what we are doing is that very simple, right? There's nothing new there, right? Assuming the three group are following the bell curve, right? How do you do that, right? So you may ask, okay, why don't we just do t-test for each pair and then we're done, right? Because we can do between 1, 2, between 2, 3, and between 1, 3, then we're done, right? And in some sense, yes, but if we're many group, then we're tired, right? So is there any better way to do it, more smart way? Okay, we call F test. So we will be comparing variance. Okay, don't worry, everything is very mechanical, and you will see the thing we do is basically using Excel to. Sorry. I hate it. Sorry. Okay, I give up. So the idea is we will be comparing variance. Don't worry. All the calculation is super complicated. So basically, what you will see, actually, you see the last year exam, and that will be, we are basically using Excel. Okay, and you just need to know how to read the output. Of course, I try to explain what they are, right? Because no one actually would actually care about how you get calculation, because the formula is already very clear from the Excel spreadsheet. Okay, but I try to give you some idea why they're true. Okay, just some bunch of formulas. One way and over. One way here, it means that very simple. One way here means every observation can be categorized by one thing, whether man, woman, or old man, right? And just imagine in CHK, everyone will have two identity. One is which faculty you are in, right? The other one is which college you are in, right? So we'll talk about one way first. Is we want to see, say, for example, we want to see if the salary of the graduate from NA is different from UC, different from CC, so on and so forth, right? So this is a question. Or you can imagine more apply is, as a company owner, you want to see is different store have different revenue, right? You want to compare once and for all, right? That's an F test goes in. But don't worry, what we'll do is we'll tell you the formula, but I don't expect you to do any calculation. There's some formula there. The calculation, I think you would expect to do the final calculation, not the intermediate, or you understand how the Excel spreadsheet answer comes out. Okay, not really expecting you to do pencil and paper for that. Okay. So as I said, you have a grouping, the gender, age, or countries. Okay, and by definition, we call each observation has a grouping. It's called factor G. G is called factor. It's a grouping. Okay. So for example, I have observation 1 is a boy. He spent $15 on $45 on lunch. He's a boy. Okay. And second observation, it's a G, right? G1 here. This is X1, right? A girl, he spent $50 for the food, and there's a girl. Okay. And the third one may be an old man, right? He spent $90 for lunch, right? It's an old man. Oh. Right? So on and so forth. Okay. So that means for each observation, I have more than one thing, more than observation, the number itself. But now I also have his grouping. Okay. Grouping is categorical. Okay. There's no meaning of the grouping. Okay. Just a group. Now, as I said, this is the data I have. And observation, each one have grouping. Okay. And how many group you have? is C number of group I have. Okay. In the case of before, C is 3 when I have man, woman, and old man, old people. Right? If in the college I have 9 in CHK, right? I think we have like 10 faculty here. I don't know. I just make up. I don't know how many faculty here. Suppose I have 10 faculty, 9 college, right? C is the number of the group. Okay. The data you have usually is like in this form, right? You'll be having the data, the non-data is actually we expect to have in Excel, right? Observation 1, how much money he spent, grouping. 2, grouping, right? Look, Excel will be like this. Okay? But I will talk about that later in Excel. So suppose I have data like this, right? I have X and the group. Okay. So I would be having, say, he spent $10, right? He's a male, it's a boy, right? And he spent $20, it's a girl. And he spent $25, he's a senior, right? Senior means old man, okay? And he is a $10, $15 is a boy, so on and so forth, right? And overall, we have n number of people, so there's nothing new here, okay? How many grouping I have? C groupings, okay? Depending on data you have. C, if C is 2, you don't need to use the ANOVA, right? C is 3 or more. So now we have something crazy notation. So that's the only difficult part is to understand the crazy notation here. Okay? The crazy notation is like this. We have sort the data by group. What does that mean? Group number 1 is called X1 what? Okay? X11 is group number 1, observation 1. Okay? And each group, how many observations in group 1? N1. Okay? And XC1 is the last group, first observation. XCNC is the last group, last observation. Okay? So this is N1 up to NC. So basically what I do is I sort people by group. I list the people in group 1 first. How many in the total of them? N1 number of people. So we just let them up. Okay? I just make them a list. Okay? Why I do that? Because later you will see why this is why this is good. Okay. So this is the raw data. Okay. And usually this is the data that we will be using Excel. Okay. It's saying that, say suppose this is NA college, this is UC college, this is, I don't know, Saul college. Okay. I have the first guy, how much he spent in the canteen, $10. This is how much he spent on the thing. This last guy, N1, so on and so forth. Okay, they not be equal number, right? N1 can be different from N2, right? Depending on how much you got. Okay, is that clear what the data is? Okay, so what I have is how much people spend on the lunch for all the colleges. I group them by college. Okay, the order here doesn't matter, but just some put them there, right? And the question we want to ask is, are different colleges, student within college, spend on the lunch, is it the same or different? Very simple question, right? I have the data of how much they spend on the lunch, right? I want to see is different colleges will have the same mean or different mean. Is that clear what we're asking? Okay, don't worry, everything is very mechanical. Excel will do the job, so don't worry about that. Okay. The first thing we have is we have been doing all the time, the bell curve, right? So underlying the UCNA, everything is bell. So this is what it says, right? And again, there are different bell at different location, right? Just go back to here. The problem we start is here, mu1 is here, right? And here I have this is mu2, and this is mu3, okay? And you ask, what is the assumption here? Assumption here, the main assumption is the big thing is same variance, okay? So this means that To do it, I make sure that this is sigma square, sigma square. Okay. But of course, when you collect the sample, will be different, the shape, right? But the underlying has the same variance. So this is the ANOVA, the main assumption. Okay. And this is usually the way you would see in many more modern texts is to assume this can be decomposed in two parts. Okay. One part is a constant, one part is a random variable. This random variable means 0. So you just separate them in two parts. One part is a fixed mean, the one part is mean 0 random error. Okay. Is that clear? So this is the way that modern statistics is how people write. Okay. Usually, this is the standard. Okay. This is just same as saying this. Okay. Same as this, simply saying that, okay, is mu1 plus everything is 0. Okay. Two part, right? So either you say total thing is a bell moved to the center mu1, or a mu1 plus some random thing is 0. Okay, the same thing. They are mathematically the same, right? Because this is normal, right? But now it means 0. Okay. Now we will be talking some notation. Don't worry. The notation will carry us not too very far. So first is all what we call the grand mean. Okay. Grand mean is just average mean of each group. Okay. So just simply go back to here. We have 3 groups here, right? The overall mean mu is just mu1 plus mu2 plus mu3 divided by 3. Is that clear? 3 groups of people. They each have their own mean, average of those. Is that clear? So just, if you go back to the more complicated question, right? We have, say, 9 colleges, right? Each college have own mean. College 1, mu1, college C, college 9 have mu9. Add them up, divided by 9. Okay, overall. Okay. And what we call is called treatment effect, where we rename. Okay. But this, what they said is, you call alpha I will be each group minus the overall. Okay. So sometimes we call it difference from the grand. Right? That's what they call treatment effect. Okay. Later you will see why I call treatment effect. Okay. So that is the case, right? Suppose I have 3 groups, okay? Man, woman, and elderly, right? And this comes from what? This is just mu1 plus mu2 plus mu3 over 3, right? Let's take this 3 number, right? Go to center. And we said the difference is called mu1, difference is mu2, and difference mu3. That's it. Okay? Remember all the bell, right? And we put all the epsilon 1, epsilon 2, 3 are the same, right? They have same variance sigma square. The shape is the same. Okay? So that's a classical property, is assuming, say, college 1 NA have this shape, everything same variance, right? And you can decompose it into this plus epsilon 1, right? Everything, right? So everything is moved in the center, okay? And alpha 1, alpha 2, alpha 3 is how it's different from the grand mean called mu. So just the notation. Now, after we have do that, so we want to come up with estimate from the grand mean, right? The first one, this is the best estimate for big mu, right? Because this adding notation is super crazy, okay? Let me go one by one what we're doing. We have group 1, group 2, group 3, right? Up to group C. First observation X11, right? X1N1, right? This XC1, this is XCNC. So what it's saying is this double submission side, okay? The outside is you group, you run over from I1 up to C, just go by this direction, right? And the next thing is you go J, second one, right? From 1 to N1, Ni. So basically just like first is 1, we're here, okay? We look at the first observation, we add everything down, right? It's 1 and J from 1 up to N1, so go this way. So you're adding this vertically, the first round. Now go to the algorithm. Now Ji become 2, right? I become 1, you just add up here, right? And now go to I become 2, you just X21 up to X2N2, right? Just go in this way. So basically what it says is you add everything there, divided by how many of them. That's it, right? Because the grand mean is just like you disregard the grouping, right? What's the mean? Add everything up, divided by how many of them? Nothing new, right? That's basically, I forgot the grouping. Average is what? That is a grand mean, right? But that's notation is like, I look at the column 1, add everything there. Go to column 2, everything there. Up to column C, everything there. That's what it said here. But no different from adding all up, right? The next one is even more simple. Sample mean is estimating mu I, right? It just simply means I add up this divided by how many of them, right? This is the mean of NA, right? And say this is the mean of the CC, right? Mean of the UC, right? Add them up, how many of them, divided by how many of them, right? The I, right? Just I is 1 up to C, right? Is that clear, the notation, what it means? Okay. Don't worry, you just need to remember what it means because we don't use the formula anyway. Okay. The formula is just telling you what it is. Try to tell you, right? Averaging all the observation there. Is that okay? And I said already that this is estimated by mu, this estimated mu I. Okay. So this example, okay, you will see the overall mean, you just add up any number divided by how many of them. Group 1 here will be add up all 4 number divided by total number of them, right? And same group 2 mean will be add up there divided by 4, so on and so forth. Is that clear? What do you mean by that? Right? I hope it's clear. So now the question is as I said, right, others have the same mean, right? So the question is actually asking, are the mu1 up to mu c the same, right? Each college have the same spending for the student, right? On average. Or are the alphas are 0? Okay. And the example would be asking, suppose a treatment, why treatment is, we have, and that's often used in medical tests, is I have different kind of medical treatment. I randomly allocate and to see it's going to be better, right? Or you can see the marketing strategy, look at different marketing and see which one goes better, okay? How do we do that? Of course, we can do t-test, but it's easier to do f-test, okay? I have 2 minutes, so don't worry. So not going to, I will talk about the formula later, but the idea is there will be a bunch of formula you expect, okay, bunch of formula. I'll talk about this next class. And then you divide them, then it will become a variance, right? And then I want to say is compare variance F-test. Okay. So what actually I'm doing, let me look at the graph. We're talking the math. The idea is very simple. The math I'll talk about later. Okay. The math is very simple. What I want to look at is, okay, is look at the how to compare the variance of two things. Okay. If you look at the F-test, what I'm looking at is later we'll call, oh, I don't have time. So it's MSG compared to MSW. Okay. MSG is looking at, difference between the mean of different group. Okay. I look at the mean of NA, sample mean, right? The number, right? So what I'm doing is very simple. Just 1 second. So basically I look at the sample I got, sample mean X bar 1, X bar 2, and X bar 3. Okay. I'm asking the variance between them. Okay. And I look at the variance within each data set. Okay. If there are no difference, the grouping has no meaning, these two variants will be very similar. If not, you will see the grouping, okay, because if they're the same, this variance will almost close to 0, right? And if they're different, right, compared to within variance, okay, then if you cannot reject, then it's an issue, okay? So I'll talk about this a little bit more on Thursday, but the main idea is looking at variance across different group and within itself, okay? And basically using the F-test, so some kind of answering that thing. But I don't want to overrun already, so I will see you on Thursday. Don't worry, we just ask you to see how to read the table. That is our goal, okay? But of course, I tell you what's the reason, but the main thing about this topic is to read the Excel output, okay? So I'll see you in next class.